Okay, everybody. So what we've got is we've got a good thing and a bad thing all happen at the same time. So we've got the idea of a random sample that we're trying to gather to get an idea of a value in the population. Okay, so what I've done is I've created these little, oops, hang on one second. Let me zoom in a little bit. So in this little number line graph, this is related but not exactly the same as one you just looked like. The parameter value you're looking for is out there in the population somewhere. Okay, and I just put it looks like about 0.5 or a little bit below. Okay, that value is out there in the population somewhere. Here are all the possible samples that you could draw from that population and the values of their averages. Okay? If you average all of these averages, X double bar is what we called it in class yesterday, that value is actually directly equal to the average in the sample. But the problem, if you look up here, you can see that a lot of the samples' averages individually are not equal to the parameters. Some are close and some are far. Close and far, again, both in quotation marks. So how do you deal with that? Okay, now there's nothing wrong with that. That's simply called, sampling error. I'm sorry about the PowerPoint. For some reason, I can't get the PowerPoint screen capture to work either with my video software. I really need like an administrative staff just to like produce this stuff for me to make it not so ghetto. Anyway, sampling error is a catch-all term. You'll hear me use it constantly in class this term. All that means is when you run a sample, your sample value isn't directly equal to the population parameter because the sample you drew isn't exactly proportional to the population you drew from. It's drawn randomly, which means you get goofy little clumps. Think of it this way. If you flip a coin 10 times, do you always get 50% heads and 50% tails? Of course not. As a matter of fact, if you did, you'd think something was wrong. You get 4 and 6 and 6 and 4 and 7 and 3 and 3 and 7. Sometimes you get 1 and 9. If you wait long enough, you'll get 0 and 10. But the thing about it is you're going to have natural sampling error. And that sampling error fills out to eventually make a bell curve, which we talked about many times. But what do you do with your particular sample? Well, the statistical idea, suppose this is your sample right here. Suppose this is your sample right here. Instead of simply reporting that sample value right there, what you do is you put left and right spread on that sample. And that is called, a margin of error, which we talked about in 243 a tad. We're going to talk about it a lot more now. The margin of error allows for greater, accuracy is the better term, because this is highly inaccurate with respect to this. As a matter of fact, if it misses it at all, it's inaccurate. So essentially what you're allowing to do is you're allowing to throw a much larger net, which then becomes more likely to catch what you're trying to catch. So think of it this way. The margin of error, left to right, is like a big fishing net. The statistic you get is the center where you throw that net, and the parameter out here is the fish you're trying to catch. If you use a large enough net, and if the sample center is quote-unquote close enough so that the margin of error spread engulfs the parameter, you will have caught the fish. It's possible, of course, that the sample is so far to one side or the other that even with the margin it misses. We'll deal with that momentarily. But the idea of a margin of error is simply that. You want to create a throw net that makes your statistic larger than life, if you will, or larger than it can be representative. And hopefully, with what is called confidence, mathematical statistical confidence, the parameter you're looking for is captured within that net. Okay, so I'm going to give you a quick little 3-step program, and then we're going to go to the board and we're going to play with an example we'll look at here in a second. So what you're going to do is you're going to construct a confidence interval from a sample. So it's a 3-step process. It's pretty straightforward. First thing you do is you draw your random sample. Now, we did that in class last week with dice. We'll do it next week with coins. We'll also do it with blindfolds and touch therapy. We'll also do it with stopwatches and butterfly times in the pool. Well, there's lots and lots of data we'll collect in this class. But any of it has to start with a random sample. Now, all random samples have slight biases to them. We try to minimize as many of those as possible. More on that as we go. First thing you do Your second thing you do, excuse me, after you draw your random sample, second thing you do is you find whatever statistic you're interested in. In this class, Math 244, the only two things we'll be interested in are either a percentage or a probability or an average. Percentage or an average. So if you're thinking about the dice we rolled last week, that's an average amount of the pips that show on the dice. The example I'm about to do with you right now is a percentage, and we'll see how that plays into. We'll get to that in a second. And the last thing, and this is really the big part of Math 244, is get the margin of error on that center, the plus or minus on that center, because that will help you more correctly or more often capture the parameter you're looking for. More often capture the parameter you're looking for. Now I want to show you an example. I'll give you a kind of a work in progress here. This is Max last year after soccer practice. Okay? We went out to dinner after soccer practice, and he loves flipping coins. He just gets a kick out of flipping coins. Okay. So he started saying, okay, Daddy, I think I can call coin flips. I was like, what do you mean, buddy? He's like, when I throw it, I think I can tell you whether it's going to be heads or tails more often. I'm like, okay, buddy, let's do it. So we started doing it, and I kept track because that's the kind of stuff I do because I'm a freak. So he got the first one. He went 1 for 1. He called heads, and it was heads. I forget exactly what he called, but he got it right. He also got the second one right. And then he got the third one right. He's feeling pretty studly. He's 3 for 3 right now. He's feeling pretty studly. I didn't bother telling him there's a 12.5% chance of me guessing the same result because I didn't want to burst his bubble. Then he went 3 for 4. He missed the next one. But then he went 4 for 5. And then 5 for 6. So after 6 throws, he had guessed 5 of the 6 of them correctly. Okay, making sense so far? Okay, then he missed one, went 5 for 7, then 6 for 8. Anyway, we continued this for a while, and then he got bored right at 8 out of 13. So he had flipped it 13 times and gotten it right 8 out of the 13 times. And he said, you see, Dad? I'm like, see what, buddy? And he's like, I got more than half of them right. That means I'm doing better. And I was like, oh, that's cool. He actually understands that if he flipped the coin 13 times, he should have gotten it right 6.5 times out of 13 on average over a long period of time. He got it 8 out of 13. His little brain processed that 8 is bigger than 6.5, so therefore he did better than guessing. What I want to do next is I want to analyze this more correctly. So we got to go to the chalkboard, do some math now. And the only math we're going to be doing is adding and subtracting. More math to come, but right now this is just adding and subtracting. Okay, let's go look at the chalkboard and then come back to this.